Okay, looks like this. It says momentum and impulse at the top. We got to the momentum, we didn't get to the impulse. And oh my, did we get to him? No. So I was A12. This is A34. This is your sheet. Looks the same. It's got the same people running into one another. But then we get to the bottom of the second page, there's nothing there. So this is what we've got to do. Telling the other class that when I was in high school, I took physics, we didn't do impulse. It's actually a really useful concept. You can get through life without it. You can do all the physics you need to just using momentum, but impulse makes it easier. So what is impulse? Impulse is a force applied over a time interval. So technically, impulse, if you want to calculate it, you just multiply a force times the time. Force, time. All of this, you don't need to draw the picture. I'm just drawing the picture because I like to draw pictures. Now let's say you've got a car and your car has stalled and you need to push this car this way to the right. And you get behind the car and you start to push it and you apply a force. You push the car with like 100 newtons of force and for 6 seconds. What's going to happen to the car as you start pushing it and push it for 6 seconds with that force? Should move, right? Hopefully. I mean, if this has got too much friction and it's too heavy, then you won't be able to do it. But what it's going to do is it's going to start moving. And it's going to gain momentum. And the important thing is, if you multiply 100 times 6, and you get 600 Newton seconds, the 600 is also how much momentum it's going to gain. So the formula relating impulse to momentum is impulse, Ft, equals the change in momentum. So you can give something momentum by applying a force for a certain amount of time. So this car is going to get 600 kilograms meters per second of momentum. If you only pushed it for 2 seconds, it wouldn't get going as fast. It wouldn't have as much momentum. How much momentum would it have? It would have 200 kilograms meters per second. So this is one way to write the impulse formula. This is impulse, force times time. And you can also write it like this. I don't know that I'm ever going to use it like this with you, but you may find this to be easier when you're solving for something. Since momentum is mass times velocity, and usually what's changing is velocity, you can say force times time equals mass times the change in velocity. If you like that, but I'm going to probably just use this. Guess what the units for impulse are? There are 2 different kinds of units you can use. I don't care which one. This is impulse. What would the units be? What? What's the unit for force? Newtons. What's the unit for time? Seconds. So you can do Newton seconds. Or, since impulse is change in momentum, we can do the same units as for momentum. And momentum is mass times velocity, so the units for momentum are kilograms meters per second. A kilogram meter per second is the same thing as a Newton second. It's kind of weird, but trust me on that. So there are 3 different ways to rearrange the impulse momentum formula. I feel like by this point, if you see a formula that's got this format where it's 2 things multiplied together equal another thing, you ought to be able to tell me how to solve for t or f or delta p without me helping you along there. But I will help you if you need help, but you should be able to do that by now. So if I just wanted to solve for time, what would it be? If Ft equals delta P, then T equals delta P divided by F. So if you're struggling with that, just put it in the triangle. What goes on top in the triangle? Delta P. And then we T, and just cover up the one you want. So if I want T, cover that up, I've got delta P over F. Oops, sorry. Can't write an F. So that would be the change in momentum divided by the force. And if I wanted to solve for F, what would that be? Cover up F, delta P over T. If I want delta P, it's just F times T, which is what I already have. So those are three different ways you can use this, depending on what you're looking for. You might be looking for any of those things. Another thing I'm going to just jump in and talk about that that I didn't mention in the other class, and I probably should have. But here's the important thing about impulse. If you can have delta P like this, force times time, you can also have delta P like this, little force times a big time. You can also have delta P like this, big force times a little time. So if you're getting in a car accident, what kind of delta P do you want? Top, middle, or bottom? If you had to choose, which way you're going to have it in a car accident, would you like delta P equals a medium-sized force times a medium-sized time, delta P equals a little force times a big time, or delta P equals a big force times a little time? They're all the same delta P.
Little force, big time.
Right. So delta P, this is about slowing you down. This is about getting rid of your momentum and maybe the car's momentum. And you don't want a big force. You don't want a big impact force. So you need to stop, what, abruptly or slowly? Slowly. So you have a big T. And in a car, what's a thing that allows you to have this kind of impact rather than this kind of impact? Airbags. Airbags lengthen the time. Instead of you just hitting the dashboard or the tree or whatever with your head and it's stopping really fast and you get a big force, you hit the airbag and that slows your head down over a long time and you get a small force. So that's kind of the most important take-home thing about force and time and change in momentum. But what you're going to be doing today doesn't really relate to that. We'll get to that later. You're going to be making things. We'll probably do an egg drop. Most of the time people do egg drop activities when you get to this. Has anybody ever made an egg drop thing before?
Yeah.
You've always won? You think he's going to win again?
I did it in Fleming.
You did it? Should we not? You've all done it. You want to do it again or no? All right. There'll be different rules to this one though, of course. All right. A couple of practice problems.
I've never known Arena. I met her this year.
If you were to just read this out of the blue, you might think this was a Newton's laws kind of problem with kinematics. So this is something we can do now with impulse and momentum that I think makes it easier. Ooh, sorry. I don't know. I wish there were a way I could intentionally focus this camera, but it focuses when it wants to. So I'm telling you in the beginning, we're going to be using this. Ft equals delta P somehow. That's where this is all going. So that formula can solve this problem. But let me show you the problem. 2 kilogram block of wood. This sounds familiar. It should. It's moving at a velocity of 5 meters per second. So its velocity is 5 meters per second, and it's going to the right, sliding this way. It slows to a stop over a time of 3 seconds. So when it gets to here, the 2 kilogram block of wood is going to have a velocity of 0. And the time interval going from there to there is 3 seconds. So we need to figure out basically the force of friction. We need to find the force that's bringing the wood to a stop. So we could use F equals ma, and we could find the acceleration, A equals delta V over delta T, and we could do this problem that way, and we could find the force of friction like we were just doing in the last unit. Or we could just use this. So we're looking for a force That's the force. We need to know the time. Do we know the time? Do. 3 seconds. Now, the only other thing we need to know is the change in momentum. So let's do a couple of things. I'm going to write PI, that's initial momentum, equals, what's the formula for momentum? This is a check. P equals what? You should have this one memorized. MV. What's the mass of this? 2. What's the V of that? 5. So 2 times 5 is 10 kilograms meters per second. Now the final momentum, what's the momentum of this thing? This is an easy one. Zero. Momentum is inertia in motion. If you're not in motion, you don't have momentum. So I could write this out. I could say 2 kilograms times 0 meters per second equals 0 kilograms meters per second. So what's the change in momentum? Momentum was 10, now it's 0.
10.
Did it gain 10 or lose 10?
Negative 10.
Negative 10 meters, or kilograms meters per second. Oh, I almost put a second squared on there. And if you wanted to write this out in a formal kind of fashion, change of momentum is the final momentum minus the initial momentum. So it's just going to be 0 minus 10, which gives you negative 10. All right, so now we're ready. We've got this. We just need to plug it in here. And the trick is, though, I'm solving for F. So thinking about the previous page, this is solving for delta P. But if I want to write F equals, what does it equal? It equals what? There's delta P, there's F, there's T. So F equals what? Not delta P. Delta P divided by T. Delta P divided by T. So I'm running out of space. I don't know where I guess I'll just crunch this in. Delta P is negative 10 kilograms meters per second. T is 3 seconds. What's 10 over 3? I know somebody can do that, approximately. It's going to be a repeating number. 10 divided by 3? 3.33, except this is going to be negative. So the force is negative 3.3, I'll just call it negative 3.3 newtons. So there's the final answer. So that's just in physics. There are always multiple ways to solve problems, and this is just a new way to solve a problem like this. You could have found the acceleration, you could have used F equals ma, and you could have solved it that way. I don't know if that's better or worse, but I kind of like doing it this way. All right, one more. I think we'll do 2 more practice problems, and then the rest of the time is yours to do what you need to do. 1,000 kilogram cars rolling toward you at 2 meters per second. In order to slow the car to a velocity of 1 meter per second by pushing against it for 10 seconds, how hard do you have to push? So can you imagine that? It's coming at you. You're trying to slow it down. You push.
You gotta push.
You push so that you can slow it down to half its speed, and you push for 10 seconds. And we're looking for force. So it's the same thing as before. I can just go ahead and write this formula. The force is going to be the change in momentum over time. So if we know these 2 things, we can figure it out. Do we know either of those at this point? Do know one. Do we know the change in momentum or the time? Time. 10 seconds. So we just need to know the change in momentum. So the change in momentum, in the beginning, it's got this much mass and it's going that fast. Can anybody just blurt out the momentum that it has in the beginning? 2, more than 2. Begins with 2. The initial momentum is, the mass is 1,000. The velocity is 2. What's the momentum? 2,000. So it's the mass multiplied by the velocity, and that gives us 2,000 kilograms meters per second. So the final momentum, after you've been pushing on it for 10 seconds, its velocity is 1 meter per second. How much momentum does it have then? So when it slows down to 1 meter per second, how much momentum does it have? 1,000. So its momentum then is 1,000 kilograms, that's its mass, times its velocity. So its new momentum is 1,000 kilograms, or 1,000 kilograms meters per second. So this is what its momentum starts at, and this is what it finishes at. Is it going to be a positive or negative change in momentum?
Negative.
Negative how much?
1,000.
Negative 1,000. So the change in momentum is just the final minus the initial, and that's 1,000 minus 2,000, which is negative 1,000. But you don't have to do that math if you can just see it loses 1,000. So we've got negative 1,000 kilograms meters per second over 10. That's easy math. What's the force going to be? What's 1,000 divided by 10? Negative 100 in this case, newtons. There you go. That's not too bad. So let me give you this practice. And this is the assignment and homework. If we don't finish in class, you probably won't finish in class. But 5 minutes you might get done. And the answers to this are on my website now. They're also in Google Classroom. And I don't care when you do this, if it looks great. I don't care if it's really complete. I just want to see that you've been through the whole thing and that you've tested yourself, because the point of this is for you to go through it and see if you can do it and figure, what, we're not done. I want to do one example with you in here. The point of this is for you to go through it, see if you can do it, and then if you can't, ask questions about it next time. So again, this doesn't have to be neat, doesn't have to be word for word like mine, but on the test you need to be able to do it, you know, with good solid answers. I'm going to add in another formula here that I should have given you, although I don't think you necessarily need it. Change in momentum just equals final momentum minus the initial momentum. That's just kind of a straightforward one. These are right in the notes. They should be. These momentum problems start out kind of easy, although 7 you might find that kind of tricky. 9 isn't too bad. It's like something we just did. 10 isn't so bad. 11, I want to do this one on the board. So just as a demo, this is a conservation of momentum problem, but I think it'll be worth me doing this on the board. And hopefully, whoever watches this, if anybody watches this, they can see what I'm doing. Hopefully you can help me go through this as we do it. Number 11 is a lot like number 12, so that's why I'm doing this. And I think both of them might be kind of tricky if you just did them on your own. Car A has a velocity of negative 10 meters per second and a mass of 500 kilograms. Car B has a mass of 800 kilograms and a velocity of 6 meters per second. If they collide and stick together, what's their shared velocity after the collision? So what should I do first? Guess what I'm going to do if I'm going to solve this?
Draw it.
I'm going to draw a picture. Now, I didn't leave you space to draw a picture. Always feel free to get some extra paper out if you need to. Oops. There we go. So I need to draw car A and car B, and it turns out, which one should I draw on the left? Should car A be on the left, or should car B be on the left?
Car B.
Car B. And the reason is because B is going to the right, and A is going to the left. So this one's got a mass of 500 kilograms, and it's traveling left, and it's got a velocity of 10 meters per second. To the left. So the velocity says negative 10 in the problem, but I'm writing, actually, maybe I should just write velocity equals negative 10. And then B is going to the right, and it's got a mass of 800 kilograms, even though it looks like that one's bigger. Maybe I'll add something to this car. There we go. And it's got a velocity of 6 meters per second. And they're going to hit to one another, or hit one another, not to one another. And then they're going to stick together. So this is car B after the collision, and this is A after the collision, and they're all messed up. Still 500, it's still 800. And we're supposed to find the velocity. So how do I do this?
You need to find the momentum.
The momentum of what? Can you explain the big picture? Because I think you're on the right track. Like, what's that?
Well, we need to use the formula P equals mv.
P equals mv we'll use a lot.
Or,
Yeah? If this before picture and this after picture, what is the relationship between those? What's the big idea that, like, what's the same about this and this? Same masses as before, but
they're still moving?
maybe they'll stop. Do you think they'll just come to a stop?
They're gonna start moving to the right.
Will they?
Slowly, yeah.
How do you know?
Because the one on the left is heavier, has more momentum.
But it's going slower.
Oh, I didn't even notice.
So this is more massive, but it's going slower. This is less massive, but it's going faster. Could it be that they'll just stop?
Yeah, if
Moment
Which one?
on the 800. Like,
Yeah.
Wouldn't it keep going though?
Well, it depends on how fast it's going.
Like with large, like with big trucks, like it doesn't, it takes a long to stop.
That's true, but if it's slow enough and this is fast enough, that's like some cornerback tackling a fullback, but the fullback's just standing there and the quarterback's flying in at 20 miles an hour. You could knock him back. So here's the big deal. This is the important thing. This is the thing you should jump to right away. The net momentum here, whatever that is before the collision, how does that compare to the net momentum after the collision?
it's the same.
It's the same. So that's the key. And how do we get the net momentum before the collision?
Adding up the momentum.
Add up the momentum. So what's the momentum of car B here?
It's 48 or 40, yeah.
It's mass 800 times 6, which is
48.
4,800 kilograms meters per second. And the momentum of A?
Or negative 5.
Negative 5,000, because it's to the left, negative 5,000. And this is going to answer one of our questions. If you add those two numbers together, what do you get?
98,000 or 9,800.
Well, no, because this is negative.
Oh,
4,800 plus negative 5,000, or 4,800 minus 5,000.
200. Negative.
negative.
Negative 200. So that answers our question about which one wins. Which one, like when they crash together, which way are they going to be going? Right or left? Because they've got momentum to the left. So this one actually has more momentum than that one does. So even though it's lighter, the fact that it's going faster offsets that, and it's got a little more momentum than this. So they're going to be going left. And the question is how fast. So now, what do I need to do with this number? That's the net momentum before the collision. What do I do with that?
You could draw or write it down in a second.
Negative 200 kilograms meters per second. This is just like those problems where you have the masses stacked on top of stuff, except you have to visualize it and draw it out yourself. So now I can solve for V using this formula, except I need to rearrange it. V equals what?
P divided by M.
P over M. You could go through the triangle thing, but momentum over mass. And now it's just like one car, so I've got one thing with this momentum, and the velocity is going to be its momentum, negative 200 kilograms meters per second, over the mass, which is 1,300 kilograms. And I did this earlier. I'll have to just cheat and look at my answer. What is so funny, Jake? Something.
That's Lucas all day.
Ooh, when I did this in the other class, I think I wrote it positive. So it's 0.154. Negative 0.154 meters per second. So it's not very fast. That's the answer. I'll stop there. So your assignment's to do the rest of